Welcome to G Fun Facts Online. Today, we are journeying into the deep darkness of the early cosmos. We often think of space as a void, but if we wind back the clock, that darkness was a canvas of swirling potential. We are going to talk about the architects of planetary systems, the hidden nurseries where moons are forged, and the chaotic, beautiful mechanism that built our own solar system. We are talking about the Circumplanetary Disk, or CPD. To understand these structures, we have to look past the stars and zoom in. For decades, astronomers have stared at newborn stars, observing the vast wheels of gas and dust known as protoplanetary disks. We saw the rings and the gaps that hinted at invisible giants growing inside. But recently, our gaze has gone further. We have zoomed past the star, past the great spiral arms of the stellar nebula, to witness a phenomenon that is a miniature mirror of the solar system itself. These are the disks within disks. They are the gatekeepers of planetary growth. To understand them is to understand the final chapter of how a planet, and its moons, comes to be. Let's start by contextualizing this. Imagine a cosmic Russian doll. A star is born from the collapse of a molecular cloud. The conservation of angular momentum flattens the remaining material into a protoplanetary disk. This is a vast, dusty frisbee spanning hundreds of astronomical units, orbiting the protostar. Within this massive disk, density fluctuations happen. A seed forms. This could be a rocky core or a gravitational instability. As this protoplanet grows, its gravity becomes the dominant force in its immediate neighborhood. It clears a lane in the stellar disk, carving out a dark annular gap. But here is the key. That gap is not empty. Gas streams across the gap, bridging the divide between the stellar disk and the planet. When this material approaches the planet, it carries too much angular momentum to fall directly onto the surface. Instead, it spirals inward, forming a smaller secondary accretion disk around the planet itself. This is the circumplanetary disk. It is a disk orbiting a planet, which is orbiting a star, which is orbiting the galaxy. The domain of this disk is defined by something called the Hill sphere. This is the region of space where the planet's gravity dominates over the star's tides. For a planet like Jupiter, the Hill sphere extends roughly 50 million kilometers. Theoretical models and hydrodynamic simulations suggest that a circumplanetary disk typically fills the inner 30 to 50% of this sphere. Beyond that boundary, the chaotic tug-of-war between the star and the planet shreds any organized structure. Now, how does this disk feed the growing planet? In the flat, 2D models of the past, astronomers assumed gas just spiraled in from the edges. But modern 3D simulations reveal a much more violent picture, known as meridional circulation. Imagine a vertical feeding frenzy. Gas from the upper layers of the stellar disk, which is less depleted, rains down vertically onto the poles of the growing planet. It crashes into the circumplanetary disk, creating shock fronts and generating immense heat. This material then spreads outward along the midplane before spiraling back inward to accrete onto the planet. It is like a fountain effect, cycling material and processing the dust and gas that will eventually become moons. This brings us to the anatomy of this moon factory. A circumplanetary disk is not just a uniform sheet of gas. It is a complex, stratified machine. Closest to the planet, we have the inner sanctum, or the accretion zone. Here, the disk is incredibly hot, potentially thousands of Kelvin. The viscous friction caused by gas spiraling onto the planet at high speeds generates intense luminosity. This region is too hot for ices to exist. Any dust here is made of silicates or metals. This is the bottleneck through which the planet gains the bulk of its mass. Further out, we find the dead zone. Here, the density remains high, but the turbulence drops. This quiet, dense environment is the perfect incubator for moon formation. Without violent turbulence to shatter them, dust grains can stick together, growing from pebbles to boulders to satellitesimals. Crucially, there is the ice line. Just as the solar system has a snow line beyond which water freezes, the circumplanetary disk has its own ice line. The position of this line is critical for the composition of future moons. Inside the line, moons will be rocky and dense. Outside the line, moons will be rich in water ice and volatiles. We see this fossil record in our own backyard. The gradation of density in Jupiter's Galilean moons, rocky on the inside like Io, icy on the outside like Ganymede, is a direct result of the temperature gradient in Jupiter's ancient circumplanetary disk. For a long time, these disks were purely theoretical. We knew they must exist because Jupiter and Saturn have moons orbiting on the equatorial plane, but seeing one was a different story. The glare of a parent star is billions of times brighter than a planet, and the planet is thousands of times brighter than its disk. Spotting a CPD is like trying to see a moth flitting around a firefly, which is itself buzzing around a spotlight. But the system PDS-70 changed everything. Located about 370 light-years away, in the constellation Centaurus, this young star hosts two giant protoplanets, PDS-70b and PDS-70c, which are carving a massive cavity in their stellar disk. In 2019, and confirmed in 2021, astronomers using the Atacama Large Millimeter/Submillimeter Array, or ALMA, made a startling detection. While Planet B appeared clean, Planet C was surrounded by a discrete cloud of millimeter-sized dust grains. This was not a glitch. It was a ring of material, roughly the width of the Earth-Sun distance, orbiting the planet. The mass of the dust alone was estimated to be about 0.03 Earth masses, enough to form 3 moons the size of our own Luna. PDS-70c is the holy grail of detection, for a few reasons. It orbits far from its star, about 34 astronomical units, making it easier to see. Furthermore, in 2024 and 2025, advanced analyses of gas velocities showed kinks in the Doppler shift data. The gas wasn't just orbiting the star, it was swirling around the planet. Add to that the observations of hydrogen alpha variability, where the planet glows brightly as hydrogen gas crashes onto its surface at supersonic speeds, and we have the smoking gun of active accretion. To study these disks is to study our own origins. The Galilean moons of Jupiter, Io, Europa, Ganymede, and Callisto are a miniature solar system, and their formation is the primary test case for any CPD theory. Take the resonant chain mystery. Io, Europa, and Ganymede are locked in a 1 to 2 to 4 orbital resonance. Theories suggest that as these moons grew within the thick gas of the Jovian CPD, the drag from the gas caused them to migrate inward. They drifted toward Jupiter until they locked into these gravitational sweet spots, which prevented them from falling all the way in. A leading theory by researchers Robin Kennup and William Ward suggests that the Jovian disk was gas-starved. If the disk had been too thick, the moons would have spiraled into Jupiter and been destroyed. They proposed that Jupiter had generations of moons. The current Galilean satellites might just be the last generation that formed, just as the gas was dissipating, saving them from a fiery death. Detecting these disks pushes the absolute limits of modern astronomy. We rely on 3 main signatures. First, infrared excess. A planet with a disk appears brighter in mid-infrared wavelengths because the dusty disk absorbs light and re-radiates it as heat. Second, kinematic signatures, using arrays like ALMA to see the velocity of gas deviate from the flow of the star. And third, accretion tracers like hydrogen alpha emissions. The James Webb Space Telescope is currently revolutionizing this field. Its mid-infrared instrument can pierce through the dust of the parent star's disk to spot the thermal glow of the circumplanetary disk. Early data suggests it can even detect chemical signatures like water vapor, methane, and ammonia, offering clues about the potential habitability of future exomoons. Looking ahead, the extremely large telescope, set to see first light later this decade, will provide the angular resolution needed to image these disks directly in optical light. This leads us to the exomoon frontier. If circumplanetary disks are common, then exomoons must be ubiquitous. While we have thousands of confirmed exoplanets, confirmed exomoons remain elusive. The study of CPDs is the indirect path to finding them. By measuring the mass and extent of these disks, we can calculate the moon budget, the maximum mass of satellites a planet can spawn. Current estimates suggest that superjupiters could host moons as large as Mars or even Earth. If such a moon formed in the habitable zone of its star and possessed an atmosphere, it opens a new paradigm for life in the universe. In conclusion, circumplanetary disks are transient, fleeting structures. They last perhaps only a few million years. Yet, in that cosmic blink of an eye, they determine the spin of the planet, the final mass of the gas giant, and the architecture of its moon system. They are the engines of diversity. When we look at the PDS-70 system, we are not just seeing a smudge of light, we are time traveling. We are watching a version of a young Jupiter, 4.5 billion years ago, spinning up its forge to create a Europa or a Ganymede. We are witnessing the universal recipe for world building playing out across the dark expanse of the galaxy. Thank you for listening to G Fun Facts Online.